All right, so today we're doing direct variation. We're going to write and graph direct variation equations, and we're going to solve problems involving direct variation. So, direct variation equations. A direct variation is described by an equation of the form of y equals kx, where k does not equal 0. The equation y equals kx illustrates a constant rate of change, and k is the constant of variation, also called the constant of proportionality. So when we look at these two problems, we name the constant of variation for each equation, then find the slope of the line that passes through each pair of points. So remember that the equation for slope is the change of y over the change of x. So when I do the change of y over the change of x, I end up with a slope of -4. The constant variation is also -4, okay? And then on the second one, again, I find the slope of the line by the slope equation, and I end up with 1/2. So my constant variation is 1/2. You can also see it in the equation of a line, y equals 1/2 x. The slope is 1/2. That also would be my k, or my constant variation. And what these types of problems are showing you is that the slope and the k, or the constant variation, is the same number. It's the same value, okay? All right, so let's take a look. How can we utilize this? The slope of the graph of y equals kx is k, just what I said. Since 0 equals k times 0, the graph of y equals kx always passes through the origin. Therefore, the x and y intercepts are 0, okay? So we want to graph this equation here, y equals -6x. We want to graph that. Well, we know that -6 is the k, or it's the slope. Then we can make a fraction out of that. Any whole number, we can make or any integer, we can make a fraction by putting it over 1. So -6 over 1. And when you look for slope, that's rise over run, okay? And when you're looking at the rise, that's going up or down. It's positive, it'll go up. If it's negative, it goes down. And my run is left and right. If it's negative, it goes left. If it's positive, it goes to the right. All right, so -6 over 1. And when you have a negative number, only one, the numerator or the denominator, is negative. The other one must be positive, okay? So we can always start at 0, 0 in this type of equation. And then if we have -6, 1, we would go down 6 spots, and then we would go to the right 1 spot, put my point in there, and then we would just simply draw the line through the 2 points, okay? And that's how I would graph my line. All right, so here's another example. We are going to graph y equals -3/4 x. All right, so it's rise over run. And since it's -3/4, one of them has to be negative. So I could say -3 over 4, okay? So my rise would be -3. I start at 0, 0 on this type of an equation. I can go down 3, 1, 2, 3, and then I can go to the right 4. 1, 2, 3, 4, and I put my dot right there. Now I just simply have to draw my line as straight as I can through the 2 dots, or the 2 coordinates. And then that is my graph of the line y equals -3/4 x. Okay? All right. So the graphs of all direct variation equations share some common characteristics. First of all, they're all in the form of y equals kx, where k does not equal 0. Also, all of the graphs that are y equals kx passes through the origin. And if k is greater than 0, then the slope is going to be positive and go in that direction. And if k is less than 0, or a negative number, the slope is negative and it goes down and to the right, okay, in that direction. And if the relationship between the values of y and x can be described by a direct variation equation. then we say that y varies directly as x. Okay? So as y changes, it varies directly as x changes. Okay? All right. So suppose y varies directly as x and y is 72 when x is 8. So the first thing we want to do is we want to write a direct variation equation that relates x to y. Well, we start out with the equation y equals kx, and then we plug in the y and the x that we know. So y is 72, x is 8. We want to isolate the variable k, so we divide both sides by 8, and 72 divided by 8 is 9, and that gives me k equals 9. So my direct variation equation then is going to be y equals 9x. So that's the answer for A, y equals 9x. Now it tells me to use the direct variation equation to find x when y is 63. So now I start with the equation y equals 9x. I plug in what I know, which I know the y is 63, and then I solve for what I'm looking for, which is the x. So 63 equals 9x. I divide both sides by 9, and x equals 7. So when y equals 63, x equals 7. All right. So suppose y varies directly as x and y equals 98 when x equals 14. Write a direct variation equation. So we have to write the direct variation equation that relates x to y, and then we have to find y when x equals -4. So go ahead and pause, try to solve this, and then come back. All right, welcome back. All right, so I'm going to start with y equals kx. And it tells me that y is 98 when x is 14. Okay? So then I'm going to divide both sides by 14, and k is going to equal 7. So my direct variation equation is going to be y equals 7x. So that's the first part. That's the first thing they asked for. Now I'm supposed to find y when x is -4. So y equals 7 times -4, or y equals -28. So these are my two answers. And that problem is solved. All right. So dealing with direct variation problems. One of the most common applications of direct variation is the formula d equals rt, where d is distance, and it varies directly as time, t, and the rate r is the constant variation. So for example, d equals rt, the d would be my y, the r would be my k, and the t would be my x. Okay? All right. So an example of that, the distance a jet travels varies directly as the number of hours it flies. A jet traveled 3,420 miles in 6 hours. Write a direct variation equation for the distance d flown in time t. So I know that the formula, again, is d equals rt. I know the distance is 3,420, and I know the time is 6. So I end up with the equation of 3,420 equals r times 6. I'm then going to divide both sides by 6, and I get 570 equals r. So therefore, the direct variation equation is d equals 570t. Okay? So the airline flew at a rate of 570 miles per hour. Now I can take that information, and it says to graph the equation. So I'm going to graph d equals 570t. We know it's going to pass through origin, and we know that it's going to have a slope of 570, okay? Because k is the slope, and 570 is in the k spot. And so we would take that 570, put it over 1, and that's the rise over the run. So we would go up to about where 570 would be and over to 1. That's going to be about right there, okay? Then we just draw a straight line through the points. And by the way, this point would be on my original where it was 6 and 3,420, and you can see it actually falls on that point. Okay, that was from question A. All right. Then we are to estimate how many hours it will take for an airliner to fly 6,500 miles. Well, that's our distance, or our D. So we plug that into D and we solve for T. So we would divide both sides by 570, and T is approximately 11.4 or 11.4 hours. Okay? All right. So here's one for you to try. Retail. The total cost of C of bulk jelly beans is $4.49 times the number of P pounds. All right, pause the video, try it, then come back. All right, welcome back. So A says write a direct variation equation which relates to the variable. So I would have C for the total cost equals $4.49 or 4.49 times P. That is my direct variation equation. All right? Now you need to graph that. Well, I know that I can take 4.49 over 1, and that's my rise over my run. So if I go up, that's almost to $4.50 over to 1 would put it right here. And I know origin. So therefore I could take this, and I'm a little off, but pretty close. Okay? So that's graphing it. Now find the cost of 3/4 pound of jelly beans. So that would be C equals 4.49 times the pounds, or 3/4. Okay? And when I multiply that out, I get C equals, or C is approximately, I would have to round that as 3.3675 or something like that. So I would round that to 3.37. So it's about $3.37. Okay? And that's how you solve it. All right, if you got any questions, let me know. Otherwise, have a great day.